Welcome back. We'll continue to talk about time series forecasting in the context of sensorization. So let me. In the last session, I discussed a lot of very basic time series forecasting methods, and we implemented few of those in Excel. I wanted to do something more fancier, right? Using some of the advanced features that are possible in Excel. Here's the data, right? As I said, the context is still sensorization. It is not the plain old time series modeling. So let us say that a sensor is sending us temperature of a pump at these time instances. So shift starts at 8 o'clock. So 8:01, 8:03, 8:07, periodically every minute. This can be made every second. And let us say that I have temperature readings from that pump for the next 30 odd minutes. Obviously, let us assume that this temperature is in Fahrenheit, right? So what we wish to do is, now we wish to understand if this is the trajectory of the temperature recorded in the last half an hour, what is expected to happen in future, right? What is expected to happen in future, and are there any actions that need to be triggered based on our forecasting, right? That's what Industry 4.0 would expect us to do. Automate this whole decision making process. But to automate this whole decision making process, I wish to understand what is the safe temperature. So if temperature crosses some threshold, do I need to take some decisions? For me to do that, let us understand some thresholds. Right. So what we are going to do is not new. We have already discussed that in the last session. However, this time we are going to use some of the features that are available to me, particularly in Excel. So why do I say that? If you look at the Excel sheet that is on the screen, you will realize a couple of more options available. There is something called analytics solver. You see this add-in, and there is something called data mining, right? So these are the two options that are available because I have purchased a license of analytics solver. It's a paid add-in, unfortunately. All right, but you should take a look at it. The features are amazing. I use that quite often. I think this is the first time I'm discussing the analytic solver add-in to Excel. But now that I have started discussing, because I find a direct application, let me explain that, right? So let us say this is data. The first model that we had looked at in the last session was exponential model, exponential smoothing, but double exponential smoothing also we discussed. So in data mining, I can go to smoothing, I can go to double exponential, right? And I can select. I will show you the dialog box, right? I'll show you the dialog box. It's already done, right? Timestamp is the time variable, temperature is the selected variable, right? All the other options can be checked. And once I hit this OK button, it will pop up the double exponential model fitted to the data that we have that is coming from the sensor. The dialog box also has an option for us to decide, should the model forecast, right? Should the model forecast future observations? So here we have said, yes, I want 10 more forecasts coming from the double exponential model, right? So let me show you that sheet. This is the double exponential model fitted to the data. Okay, so you can see this plot. I hope you can see this on your screen. So the red line are the actual data points that we had that were available to us. The green line is the forecasting done using the double exponential model that the analytical solver in Excel is trying to fit to the data. Okay, let me kill this for now. Right. So this is the summary. This is the fitment of the model. This is the timestamp 8:01, 8:03, 8:07, 8:09. Those were the timestamps for sensors to push the temperature data. This was the actual data, and this is the predicted data, right? From the double exponential model 104.05, 104.05, 104.185. Right. Let me increase this a little bit. Right. How good are these number? How good is this model? How good is this double exponential model? Well, the Excel add-in also prints the performance indicators. We all know, we know most of these performance indicators, right? So SSE is sum of squared errors, MSE is mean sum of squares errors, right? MAD is mean absolute deviation, right? All those indicators are printed for us to decide whether we think this is a good model or not, right? Now, fine, double exponential model was fitted, right? Now, I don't want to stop, right? The purpose of this exercise is not to fit a double exponential model and check whether this double exponential model is good. I can look at all these MAD, MFE, TSE numbers and say, this is a good model. This doesn't help me. This doesn't help me take the decision, right? I want to understand, yes, these are all 30-minute data that I have collected. How is the data going to look in future, right? And more importantly, do I have to worry about this? So the Excel solver or the analytic solver that we have also prints the forecasted values for us, the next 10 forecasted values for us. 107.17, the last value here was something in the range of 106, right? 106.74. Apparently the next value is going to be 106.71, 106.796, 106.874, all the way to the 10th forecast being 107.42. All right. And these are all forecasts. These are all predictions. Which means that predictions can go wrong. So the analytic solver also calculates the standard deviation for each of these predictions, right? What are the equations used for these predictions? I encourage you to read up on analytic solver, right? Analytic solver has amazing help menu, right? And it has all the mathematics available, so that the whole purpose is mathematics was already explained in the previous session. So let's not get bogged down with mathematics. Let's get into some nice results, right? Okay, so these are forecasts and these are the available errors with these forecasts. So 0.366, 0.474, 0.62, 0.79 and all that, right? So what we see is the standard deviation or the error expected in forecasting actually increases. Error increases. Why is that happening? Because the 10th forecast is that much farther away in future. The first forecast is immediately after the 30-minute data that we have, right? How many observations? Some 17, 18 observations, right? 18 observations. So the first forecast is immediately after that. So the expected error is anyway going to be smaller, 0.366. Whereas the 10th forecast is deeper into the future, much farther away, and therefore the expected error is going to be larger, which is reflected in the lower confidence and the upper confidence numbers, right? Upper confidence intervals. So the lower value here is 106 and the higher value is 107.43. The mean value is 106.71. Right. So between 106 and 107.4 and the expected value is 106.7, which actually is pretty much at the center. Right. Now, if you go to the 10th forecast, the expected value is 107.42, which is not very far away from the first forecast, 106.71, 107.42, not too much. But look at the lower limits and upper limits. Lower limit is 103.03. The upper limit is 111.81. Right. So you can see this funneling. Of forecasts. The deeper into future we forecast, the more careful we should be. Right. And which is reflected in this plot here. The blue line is the actual forecast. This is the blue line, and blue line is the actual forecast. Alright, so this blue line is the actual forecast, and this is the upper limit, this is the lower limit, and essentially this is the error, and you can see this error is increasing. This is called the fan model, right? Like a tunnel or a fan, the values are actually increasing. Okay, so this is what is predicted from a double exponential model by analytic solver of Excel. How does this help in decision making? Now, when the temperature of the machine, the temperature of the pump to which the sensor is attached, it goes so after the 17th value here. It is going to then record the values, right? Now, as long as it almost matches the forecast, I'm okay. I will actually be also okay if the recorded temperature is in this range, 106 to 107.43. If the fourth actual value after the 17 data points, if the fourth actual value is between 105 and 108, I will be okay. I will write my my PLC code, my programmable logic controller codes in such a way that it should monitor the temperature as long as the temperature is in the range predicted by the double exponential smoothing model. I will not take any action. Otherwise, the PLC will trip the pump saying that the pump is heating up or the pump is doing something wrong, right? Probably most likely what will happen is I will probably ignore the lower limit. I will focus only on the upper limit since the response variable is a temperature. I don't want the pump to get heated up. So I will only probably look at the upper limits and say that, well, at any point of time, if the observation crosses 109 or 108 or 110 or 111, the PLC will actually trip the pump and the pump will shut down, right? And that's how we will achieve decision making based on the sensor data that we have collected. Now, for that to happen, we have to be convinced that double exponential model was a good model to fit to the data, right? How will we conclude that? We will look at the performance indicators. We look at the performance indicators and see whether this SSE, this MSE, this MAD, this CFE, right? This is acceptable to us. If this is acceptable to us, then we can actually use this forecast to decide whether the pump should continue running or pump should not continue running, right? If we think that double exponential model was not a good model, we can choose, right? We can choose. So let me go to data mining again, right? Let me go to data again. And I can choose instead of smoothing methods, instead of double exponential, I may try moving average. I may try Holtz-Winter, right? All these we have seen. Remember when we discussed Holtz-Winters, Holt-Winters will combine the trend and the seasonality model. We have seen Holt separately, we have seen Winter separately, and remember what we had discussed at that time. We had said some of the time series are multiplicative time series, which means that the trend component and the seasonality component gets multiplied to give us the final value. Sometimes the time series are additive time series, and therefore the individual component gets added up to give us the final value. So depending on whether our time series is a multiplicative time series, whether our time series is an additive time series, we can actually run these models, Holt-Winter models, right? We have seen exponential, we have seen double exponential, we have seen moving average. So if we are not happy with the performance indicators that are provided by double exponential, right, it will always give us the graph. If we are not happy with these numbers, we can select a different method and go with the forecast picked up from that method, right? Smoothing methods, right? We can also run Arima models. We have seen these models, right? Well, we have not seen Arima models. We saw ARMA models. Once again, just a quick recap. You know about these models, right? I'm only talking about the context now. What is the difference between ARMA and ARIMA? Is that I term, right? The difference is the I term. So what do I mean by that I term? So your ACF, your PCF, your correlation factors, the partial correlation factors, right? All those will tell us whether ARMA is better, ARIMA is better. But what is ARIMA? ARIMA, the difference is this I, right, which is integrated. What is Arima? Arima is actually autoregressive integrated moving average. Why is that I there? I was not there in ARMA model that we have seen in the last session. Right? We briefly mentioned Arima, but we did not actually put up the equation for Arima, because we did not put up the thing for I is integrated. So what gets into the model is actually not integration, it's actually opposite of that, it is differencing, right? So the terms that are added there are some terms that are coming from autoregressive model, there are some terms that are coming from moving average model, and there are some terms which come because of differencing, right? Differencing. So ARMA was characterized as ARMA PQ. ARMA PQ because P is the lag from autoregressive, Q is the lag from moving average. ARIMA is indicated by three parameters, not only P and Q, but it is generally represented as P, D, Q. D tells us how many differencing differencing values do we have in our equation, right? So that is the difference between Arima and ARMA. We saw the equation for ARMA last time, therefore let's not repeat that. Let's actually go to Arima and run Arima model. Once again, all you have to do is select this dialog box, fill up the values here, right? Fill up the values here. They are actually already done because I just now finished running the Arima model on the data, right? So here are the values, right? P, D, Q, right? Here I have said select two values for autoregressive part, two values for the moving average part, and 0 for the differencing part. So we are almost like running ARMA because there is no differencing component here, right? But we can select these components. How many components from P's and how many components from Q's and how many components from D, right? These are the default values. We can change that. But let me not do this. Let me show you the results, right? Let me show you the results. This is the Arima forecast. So so these are the forecasted values, right? The 10 forecasted values, and these are the lower limits and these are the upper limits. The nature of the forecasting is still going to be the same. The forecasting immediately into the future is going to be less error prone. The standard error is going to be only 0.1, whereas the standard error in forecasting the 10th value is 0.93, which is almost 9 times more than the standard error for the first forecasted value. The lower limit and the upper limit are printed here, and those are actually drawn here, right? Those are actually drawn here. So very expectedly, let me show that again. So as we go deeper into the horizon, as we go deeper into the time, as we go deeper into the future, the upper limit and lower limit are going to fan out. So this is what we call as the fan model. Standard error is here is bigger than the standard error here. The blue line is the actual forecast, the average forecast value predicted by the Arima model. Okay, so the interpretation of the results are the same. This time we have tried to fit a Arima model, right? So here a summary of all the output printed by analytic solver, right? And it has all the statistical indicators for us to understand whether this model is a good model or not, right? So all the p-values are printed. AR1, the p-value is 0.5, not so great. AR2, however, the p-value is 0.005, which is amazing, right? MA model did not fit well, right? So all those are printed, right? You know how to interpret these values. So all the statistical indicators are printed, and this is finally the forecast predicted by analytics solver Arima model. So we have seen two of these models, right? What if I don't know which model to select? What if I want to say that, well, I don't know. So let me go back to data, right? Let me go back to data, and I said, well, we tried double exponential, we tried Arima. Which model should be better? There is a predict option. And once again, I can use linear regression to predict. I can use nearest neighbor. I can use regression tree. I can use ensemble method, bagging, boosting, right? Random trees. I can try each one of these methods to understand which gives us better results. By the way, we saw a very basic linear regression for a trend model. We have not seen decision trees. We have not seen regression. We have not seen neural network. We spoke about bagging and boosting and so on, but we did not actually see the math for it. Let's not go there. Let me take the easiest option and allow Excel to decide which is the best model, right? So I want Excel to print all the results, and then I will select which model I want to pick, right? So here is the best model, right? So find best model. So Excel will actually run all the models for us, print all the performance indicators for us. We will read what are the performance indicators, and then we will decide which performance indicators are better suited, and then we will say, this model is the best, right? So once again, the dialog box, it's already all the things are already put up here. The selected variable is timestamp, the output variable is temperature, right? All this thing is already done. There are 17 observations. The focus was not on printing large data sets, right? That was anyway indicated. You can complete all this, right? should the Excel print results for all of these, or you want to skip some of these. We can actually we can decide the parameter, or we can allow Excel to decide the parameters, right? So fit or intercept, right? All those options are available, right? So we can change all these parameters. So these are the basic default parameters set by Excel. We can change all these parameters for each of these methods. Okay. So we will simply hit the finish button there, and Excel will print this kind of output for us, right? So it has run all these models. Linear regression it has run. It has run neural network. Actually, decision tree and nearest neighbor don't make any sense for this kind of data. Obviously, right? From the data itself, we knew this methods were not as appropriate, but we anyway selected. We didn't change anything. Bagging was applied, boosting was applied, random T was applied, and these were various performance indicators for each of these methods. So in terms of MSE, RMSE, right? Let us take RMSE. In terms of RMSE, random tree and bagging almost similar, actually same results. However, if you look at R squared, 0.999, which is the best result which comes from boosting. So depending on which performance indicators we want to go with, we will then select that particular method, and then ask Excel to forecast using that method. So instead of selecting double exponential first and then Arima and then going ahead, here is a consolidated result which tells me that if I go with regression, I'm going to get a maximum R squared of 0.82. However, if I go with boosting, my R squared is going to be really amazing. If I, on the other hand, if I want to minimize the RMSE, 0.02 RMSE, yeah, RMSE is also pretty good. RMSE is also pretty good. So why don't we say that, well, boosting is the winner in all this, right? So yeah, didn't realize that, but boosting seems to be the winner in all the performance indicators. Almost, yeah, boosting seems to be the winner in all this, and therefore then we should go to predict and run a boosting algorithm to generate the forecasts for our data, right? So this is essentially being lazy and allowing Excel to print the results for us from which we can select, right? So this is okay, it is doing something funny. It's okay. So these are all the output generated by so this was the most important table, right? Most important table. Obviously it is going to have further work for us, saying that now that you have selected boosting, you apply boosting and then get results, get forecasts and all that, right? So the idea of this session was to show you that a lot of things can be done if you have nice add-ins to help you. The mathematics and the basic conceptual discussion was already done in the last session. This was more data circus session where we ran three things: double exponential, we saw the output and we saw the forecast. We ran Arima, we said this is different than ARMA, which was already discussed in the previous session. And then since there was an option of asking Excel to tell us which one is the best method, find best method, and we allowed Excel to tell us which one is the best method. Boosting turns out to be the best method, and therefore then the things becomes easier. We can go to predict, we can go to ensemble, we can go to boosting, right? This is the dialog box for boosting, and essentially run the data on this and get the output, and essentially finish the forecasting using boosting, right? So with that summary, let me end this session.